So good morning and welcome to the class of discrete math. So this is the second class from the end. So the next lecture will be the last one. Today we'll discuss the first half of the class. We'll discuss a tool in Python which is used for graph analysis. And this tool is called Network X. And after that, we'll tonight I will post the third home assignment, which will be programming in Network X. And it will be not so hard, it will be just for, say, 5 days or something like that. So please stay tuned and we begin the lecture for today. So I hope you see the slides. So you're on the big blackboard in the class, and on Zoom they're also available. So what is Network X? Well, it's called network analysis, but we all know that networks are actually graphs. So in a graph, we have nodes, or we call them vertices in discrete math and graph theory. There are edges between them. And in a network, the nodes represent real nodes of the network. So that can be people in a social network. They can be nodes in a computer network like internet, stuff like that. And edges represent connections of nodes onto each other. So an outline for today, for the first half of the lecture, is as follows. So we start from one important thing, the model of social network graphs. And we'll discuss some, well, today there will be an element of non-mathematical part of this course. We'll discuss some specific properties of social network graphs. So the study of social networks is called social network analysis, SNA. Well, it's a specific sort of graph theory, and it's a border of discrete math and, I don't know, sociology, maybe, the study of societies of people. So vertices represent actors. Well, they could be people, they could be some social entities like, I don't know, states, organizations, even maybe social events like parties or rallies or something like that. And edges, they're also called links or ties. They're various relations between actors. There could be different types of relations like friendship, I don't know, membership in a group, citizenship in a state or something like that. So sometimes they are unoriented, indirected, like, I don't know, relationship of friendship. It's usually symmetric. It could be asymmetric and therefore directed. For example, notion of subscription or knowledge. So many people are subscribed to a celebrity, but the celebrity even doesn't know that. And the standard example, which will be a running one, is the friendship relation. It's an undirected graph as we're used to. And also it's not a multigraph and not a pseudograph. So when we're talking about friendship, you cannot have two friendships with another guy. The friendship is just one edge between two people. It either exists or not. And also we usually do not consider ourselves friends of ourselves. So A is not a friend of A. So we're talking about parameters and what are graph parameters? So for a graph, you can count for, I don't know, for example, the diameter, the maximal length of, so I don't know, the maximal distance between two vertices, which is, there was a rumor that it is something like six handshakes, stuff like that. You can count something more interesting, which we'll see later on. And we're going to get acquainted with the specialized Python library for calculating this. So, and maybe an interesting part I will just show you today is that as the graphs of social networks, they have some specific behavior which can be captured by calculating these parameters. And this is important because if you compare it to a random graph, for example, then these parameters will be different. Despite that this random graph was supposed to be generated to imitate a social network. This makes social network analysis sometimes quite hard. When you try to model a social network, and there is a buzzing example now when you model the propagation of the virus, you usually don't have access to real data because it's privacy. You don't, Facebook will not give you, say, friendship network. But you want to model it using some randomizer. You want to give a random model. and you fail because the parameter of this model will be different than the parameter of the real social network. And we'll see it on running real data examples today. So these are going to be clustering coefficients, and we will discuss it later. So it's tightly connected. There is this 6 handshakes and also the cluster, which we'll discuss a bit later. The diameter is something that's 6. So in the examples, we'll use what is called SNAP dataset. It's Stanford Network Analysis Project. The dataset is available freely. I will give you the link on the course's webpage. And the dataset includes the following. So this is not, so it was taken from Facebook, but it's not, of course, the whole data of Facebook. So for 2 reasons. First, it's anonymous, of course. And the second reason is that it's privacy. Even if you anonymize the people, if you get the whole graph of Facebook, of friendships in Facebook, the friendship patterns of people are usually sort of unique. So if you consider a person and his, say, close relationship, friends and friends of friends, then using this pattern, you can localize him inside the graph. And this means that if you obtain the complete Facebook data, then knowing, say, your neighborhood cluster, you will manage to locate it inside the graph and align it, and then actually just get the data of all the people in the world, which is violating the privacy. So here, this is a part of the Facebook network, which is called ego networks. So they have taken 10 people. Of course, they're all anonymized. We don't know who are they. Potentially, they are the people from this Snap project, actually. And their immediate friends. And then the graph includes friendship relations between these guys. So these people, these 10 people, they are sort of related with each other somehow. So there are connections maybe between them, and also non-trivial intersections of these friendship networks. But it's all only a part of the graph. So it's a union of 10 ego networks of the person and his immediate friendships and friendships between these people. So this makes the data set relatively small, does not violate privacy, at least to some extent, and we can use it. And the data is, of course, anonymized. So this will be a model of part of a social network. Of course, it has some biases because ego networks, so these guys will have specific roles. They will have more friends than other people in these ego networks, just because we count all the friends of this guy, but not all the friends of other guys. And in the home task, you will see this. So network X is a Python library for graph analysis and visualization. So it can visualize your graph if you wish. It's free software licensed under BSD new license. It's capable of handling big data, like 10 million nodes. And this will roughly see 100 million edges and more. So it's really usable. It's highly portable and scalable. So how to obtain it? Well, you can use pip, this standard Python gadget for extending your Python library set. You install network X, and you also install these two. So these guys are used only for visualizing. So if you want just to do some computations, you don't need this. But if you wish to visualize, you will need to obtain this. This is just standard plotting libraries. Maybe you have already them installed. And then you import your network X as, well, I use the short name NX because I will use it frequently, but it's just the same as network X. You import this module and you use network X. So how can you define a graph? Well, let's start with the things you usually don't do in big data. You define the graph manually. So you instantiate a new graph, which are called my graph, and you add the edges just manually. So this is an undirected graph. This means that edges are just unordered pairs. So here they are ordered, but if you edge both BA and AB, this will result in only one edge. AB, BC, CA, BD. 4 vertices, 4 edges, fine. So the type of these objects can be arbitrary. So we get the benefit from the fact that Python is actually an untyped language. So here you can, we denote that by strings. Just we gave names to our vertices. In the data set, for example, they will be just numbers. So the vertices are numbers, and the library automatically adds a vertex into the graph once we have added one edge to it. You can also add it just as a node, as an isolated one. We will not need it here. So network X can also handle other types of graphs, directed graphs, multigraphs, etc. So for example, if you use dgraph instead of graph, you can use your directed graph. Also, they can be weighted. So weighted graph means that on your edge, you will have a number, which, well, usually it's from 0 to 1 as a probability measure, but it can be arbitrary, of course, which is called the weight. So, for example, if you consider a road map, then the weights can be the capacity of the road, so the number of cars it can run on that amount of time. So this means that, or the money you need to spend to traverse it. So this can be used, for example, when you try to find an optimal path, you have to spend some money on petrol, but also some roads are far, you have to pay a toll. So this means that the road can be fast, but nevertheless you have to spend more. So this is the weight. And the weighted graph, it's the time and cost of the road, and it's just an optimal parameter of at edge. Sorry, it came somewhere here. It's going to be something like comma and the weight here. So sorry, increase the size of the font and things like this could happen. So network X is also capable, of course, of reading graphs from databases, from files in many ways. So in our data set, it will be just a text file, which includes the edges of the graph just as pairs of vertices. So the easiest way. And it's just, this file is called Facebook combined.txt. It is downloadable from Snap, and you just read edge list. This is the method that reads your data set from a file. Of course, there are many other ways of doing it. Usually you use a database. And from database, you somehow obtain your graph. We will not discuss it now, but in the library official manual, you will, of course, find it. So next part. So far, so good. So what have we done right now? We have written our graph into the we have read our graph from a file and obtained a graph as a data structure in this network X. So what can we do? So of course we want to compute something or maybe modify the graph or something like that. But first let's talk about visualization. I won't show it on the running example, just on the slides, but it will be sufficient. So the first thing you can do with the graph, which is extremely valuable if the graph is small, if it's just manually inputted, just to visualize it. So what can you do if you have a large graph? We'll see in a minute. So graphs are abstract objects. They can be represented geometrically. And you can see how the graph looks like. This is done by visualization. Network X can do it even in 3D, but we'll do it 2D pictures by now. So it uses matplotlib, Python library for plotting. So it's called draw network X. So, and then you save your figure inside your PNG file, for example. So this is an example. This actually is my graph, which we defined before. So this triangle and another edge. And this is a visualization. It looks quite nice, and it's maybe useful for, I don't know, teaching school kids graph theory or something like that. But for real data, of course, this is just toy. So a directed graph is visualized as follows. So notice, yeah, we have implemented a dgraph, actually by the same thing, but notice that here, I don't know whether you can see it on the screen, but definitely you can see it on the slides. So the output of network X says that this C and B are connected dually. So usually we draw it just as two arrows. Here is just bidirectional arrow. Okay, so now if you want to draw a big graph like this Facebook EchoNet, of course, you do not wish to draw any annotations, any names of the vertices, because there's a huge amount of them. So we say with labels false, and it's it is the graph of Facebook Echo Networks from Snap. And visualization does the following. So you can see that here you don't see basically individual nodes, well, except for maybe for these ones, but you have you see the clustering. So you see a sort of a general bird eye picture of the graph. So what happens here, you see that here's some sort of cluster, here is some sort of clusters, here is a sort of cluster. What is these? These are these people who are friends of two. So we have, recall we have ego networks, so we have 10 guys, there should be 10 of them. I don't know whether you see 10 clusters here, but there should be 10 clusters. And these say are tightly connected. So potentially these people are close friends by themselves. Close means not only friends of themselves, but they also have many mutual friends, and these friends are here. This is a guy who is a bit lonely, and but he's connected to here, so we can see some general picture of the graph and the visualization. This is not something mathematical or formal, but it's sometimes useful to get the idea of how your graph looks like and what sort of algorithms you should apply to it. People, for example, in linguistics like it when they talk about classification of languages. They have some parameters, they find some relations between languages, and they get all these clusters which correspond to, I don't know, families of languages. You will see that, for example, Russian, English, German will go to one cluster and say, I don't know, something like Chinese and its variants will go to another cluster, and they will be distinct. You will see that. While seeing this from raw data, just from numbers, it's usually problematic. You have to, the visualization is usually nice. This is also output of network X, drawn absolutely automatically. And now the most interesting part, which we'll see on the code now, is graph parameters. So network X provides a convenient interface for algorithms on computing something on the graph. And now let's, well, we can see it. Yeah, let's first see the slide, then I will show the code. So the global parameters of the graph, I don't know, like the number of vertices, like the diameter of the graph and stuff like that, are just functions of the graph. So for example, this we will go to this in detail in a minute. So please just now believe that this is a parameter. So what does it mean? There is an average clustering coefficient, which in some sense calculates how much the graph tends to cluster. So for example, if your graph is, I don't know, the complete graph on n vertices, it has just one big cluster. So it does not tend to cluster, does not tend to separate in clusters. But this graph tends to. So the clustering coefficient will be different in different graphs. So how to calculate it, we'll see it on the code just in several minutes. But now let's just see the idea. The idea is that social networks, real social network data, tends to cluster much more than, say, random graphs on the same set of vertices. Or than all the sorts of regular graphs you can think about, just, I don't know, a cycle or a complete graph or an empty graph or something like that. So and this is measured by a number which is calculated from the graph. This calculated just using the degrees of the vertices. We'll see it now. So in network X, you will just have an average clustering, which is the thing like that. So another example, suppose we want to check the 6 handshakes hypothesis. So what is 6 handshakes? It means that any 2 vertices are connected by not more than 6 edges, a path of not more than 6 edges. So there is a parameter which is called the diameter of the graph. The diameter of the graph is the maximum of distances between pairs of vertices. So for each pair of vertices, of 2 vertices, we calculate the thing called distance, which is the shortest path between them, the length of the shortest path in the number of edges. And then we take the pair of vertices which are most far from each other. So, and this is the diameter, and we say that it is less or equal than 6. Again, you can compute it in our graph and get this. And our calculation here yields quite long because it's quadratic. You have to check, or maybe even cubic. Well, I suppose they managed to do it in quadratic time by some traversing algorithm. So it takes quite long, even for this small subset of the Facebook data, but it yields 8. So why did this happen? Well, it happened because it's not real Facebook, it's ego networks. So we missed some of the short paths, maybe. So this is the explanation. It's quite a good approximation of the 6 hypothesis. But on the other side, it doesn't give you any sort of gist of this small world because, well, there are only 10 people and you have 8 as a distance. Well, it could be actually infinity. Because if you take ego networks of people which are in no way connected, so this means that they're just strangers from different continents, they never knew each other, they're not friends of each other, then this would yield infinity because there could be just different connected components. So there are no intersection between them. This is about ego networks. But if you take the whole Facebook graph, you are supposed to get something like 6 because they will be connected through some people which you don't even know when you start this search. So 8 is a good result here. So there is a function called eccentricity, which is sort of local analog of diameter. This means that this measures how far from the center of the graph a given vertex is. So, and then you calculate this. For each graph, you find out this eccentricity, and then you can calculate the diameter. And then you can pre-calculate your eccentricities and make your calculations a bit faster. So the distance is the shortest path length. So this is exactly the shortest path length. And in directed graph, the path should also be directed. So sometimes the distance from A to B is not the same as the distance from B to A. It could happen in road maps when you have one-way roads. Again, you have different distances. So this is a caveat. If there is no path, then network X throws an exception. So first you have to check whether the path exists. If not, then this is formally infinity. Network X throws an exception. I can also get the shortest path itself, which is given as a list of vertices. Well, you say that you should have actually put A here, because there could be many shortest paths. A network X gives you some of them, just the first is fine. So. And traversal algorithms are represented as generators. So when you give a path, you just have an iterator over the vertices. So you can do pre-order DFS, stuff like that, all the things. So the idea is that network X provides a sort of convenient environment for doing graphs. So this is an example how it tries to start from C, and in the depth first search, draw all the vertices, and it will be the following result. More information is in the network X documentation. When you will do a programming task, you're invited to consult with that and use it when you need it. And good luck with the assignment, which will be assigned tonight. So now I'll stop sharing of the slides, and I will open the it's called network X. I will open this first. I will show the Facebook combined one. So let me show it also here. Share screen. Where is it here? So this is how the data look like. So you can see that here you will have all these pairs of. So in the middle, for example, you will have something like 67, 100, 109. That this means that guy number 67 is connected to guy number 109. So and there is something like 1,000 lines inside this. So we have. So no, it's much more. So we have something like 1 or 2 thousands, I think 1,500 of people, and we have something like more than 10,000. Many lines in this slide. You can see it. We'll calculate it using network X, so it's 88,000 of connections, which means that this graph is quite dense. So because if we have 1,000 of people, then the maximal possible number of edges is somewhat quadratic. So here it basically tries to reach it. We'll see it just now. So and now let me open another file, which is acc.py. Sorry, it's a bit spaghetti code here, but it will just written for a scratch. So we import network X. We also import random. This is the random number generator. We will need it for random graphs. So we read the data from the data set as we discussed here. So we know type as integer. We create it using an NX graph, and I think these two guys are actually optional. If you don't input it, they will just guess about it. And you input it from the text file. So first, just for checking, we print the number of edges, we print the number of nodes. We'll show it how it works in a second. So then I've also kept it in some stuff like that. So please disregard this task one. It was a task for another installation of the course. So, okay, let's calculate the maximal number of edges. Maximal number of edges is the number of nodes multiplied by number of nodes minus 1 divided by 2. Is the number of edges in the complete graph. Suppose all people are friends. So this will be the number of friendships. And this is the probability of an edge. So how likely is the fact that two guys are connected? You take the whole number of edges, actual one, and divide it by the maximal one. So this is probability of an edge between two randomly taken people. And now I calculate this average clustering coefficient. Well, it's a bit of mysterious here because we use this internal function. Now we calculate it alternatively just by hand. I will show you how it works. So what happens here? We calculate the local clustering coefficient, which says the following. So suppose there is a guy, and we consider the friends of that guy. And okay, let me even stop sharing this and share a whiteboard. Let me make it a bit more. So suppose you have a guy, called him A. Oh, sorry, it's something crazy. You have to write it. So you have a guy, you call him A, and you consider all his friends. So here are going to be a guy called B1, B2, etc., BK. So now you calculate the probability of these two guys to be friends. So what is this probability? It's so you are thinking about edges of this sort. So which make triangles. This is a triangle. What is the trick with this local clustering coefficient? So it's actually the number of edges. So this local clustering coefficient of A is the number of edges inside this, among this B1, BK, divided by the maximal possible, which KK minus 1 divided by 2. Okay? So this is the probability of an edge between two friends of A. And the trick is that usually in real social network data, this probability is greater than the general probability of an edge. Why? Because if you are friends of one person, you are more likely to be friends between each other than if you are not. So this is the property of social networks, which will not be the case for just arbitrary or random graphs. Because if your graph is random, then nothing like that happens. In a random graph, you just put your edges randomly, and this probability doesn't happen. Or for example, in a complete graph, this also doesn't happen. Or for example, in a cycle, this never happens. Because in a cycle, if your graph is just like this, then these two guys, so this is a guy called A, these are two friends of him, but they are never mutually friends. So this anti-cluster. So this is how the clustering coefficient is computed. Then you take just the average over all the vertices. Well, there are some tricks which happen. Well, what should you do if your vertex is isolated or if you have only one friend? If you have only one friend, you fail to compute your local clustering coefficient just because you have to divide by k minus 1, which is 0. And this is exactly the case because there's only one friend and there is 0 divided by 0. So these vertices are usually ignored in calculating this average clustering coefficient, but they can be ignored in various ways. So that's why we'll get a bit different results, but they will be close to them. So now let me again share the file. And you can see here that we do exactly that. So for each vertex in the range from 0 to nodes minus 1, we well, basically, yeah, it would be better to range among the nodes of the graph, but we did it like that because it's just the same as numbers. Now you take all the neighbors of this guy, of I, and you take all pairs of neighbors, and you calculate edges is the number of edges among the neighbors of this I. And then you just divide it by the total one, and we didn't multiply it by 2 because we counted each edge twice. Because here we did not check for, so if J1, J2 is an edge and J2, J1 is also an edge, so this edges is actually the number of edges multiplied by 2. Therefore, here we didn't divide this by 2. And then we just take the average, which is the, so we sum all them up and divide by the number of nodes. And we calculate it as the average clustering coefficient. So what happens next? Next, we want to generate a random graph. And the random graph is as follows. We take I from 0 to k, then we take j from 0 to I, and we edge an edge between vertices I and j at random, with the probability of the edge of the original graph. So this is called the Erdős-Renyi random graph model, invented by Hungarians Erdős and Renyi. Erdős was one of the famous people in discrete math, and by the way, his name is also connected to graph theory with the notion of Erdős number. So you take the graph of co-authorship, and you calculate the distance from yourself to Erdős. And this means how close to the center of the mathematical world you are. For example, for today, usually the number is something like 3. For example, my Erdős number is 3. For the older generation, there was like 2. Be good mathematician. You have to be co-author of a co-author of Paul Erdős. Why did they take Erdős? Because Erdős published many papers in co-authorship. He was very generous in sharing his ideas. So the Erdős-Renyi model is the easiest model of random graph. You just independently put randomly your edges with some probability. And the probability here, the idea is that the probability is taken from the original social network. So we try to make a random graph which has the same sort of density as the original social network, but it will have different properties. So again, you publish a number of edges and you calculate the average clustering coefficient. Okay, so this can be removed. Save, and now let's try to run it. Okay, so try to make this. Okay, so I will share this small window. Share. So here we have this file, and we start. So, Python 3, acc.py. It thinks for a bit of a while. So you have this number of edges, this number of nodes, 400. 4,000, so it's not that dense, it's not 1,000, it's 1,000. This is the average clustering coefficient computed by the library itself. This is the ACC we computed by ourselves. It took more time, and it is a bit different from the original one. Well, it's just because of these tricks with the vertices which are isolated or have only one friend. So there's a bit of difference, but 4 digits are the same, so it's basically the same. So this is the average clustering coefficient. Now we talk, and the network X library took less time to compute it because optimized, and we just did some brute force loops and stuff like that. And now we implemented a random graph, so this will be different. It has the same number of nodes. It's a graph on the same set of nodes. So the number of edges is basically sort of the same. It's a bit less, but it's just because it's random, it could be bigger. And now we calculate the average clustering coefficient. It's much less. So this shows that your graph is not this, is actually a different one. So it has different nature. For modeling social networks, you will have to use a different sort of graph models. So for example, like Watts-Strong's or something like that. So this was an introduction into network X. So I will announce the question, what will be for your home assignment. The question will be like that. You will have to actually find out these centers of the ego networks, of the ego, of these guys that were the centers of the ego nets inside this data set. And I will show formally, I will show it in the formulation tonight. So again, the deadline will be something like next, I don't know, even not Wednesday, maybe even Tuesday. So because the assignment will be really an easy one, just an example on ego networks. So this is the end of the discussion for today of network X. So as you can see, it's quite an intuitive, well, hopefully intuitive library for discussing for modeling graphs networks in Python. So all the things are just pronounced as in English. So you say number of edges or something like that. And the second part of today's lecture is devoted to we continue talking about NP completeness, but we're also talking about graphs. So we'll show NP hardness of another well-known problem, which is actually famous, the Hamiltonian path problem. So this is to show the method. I will, so we have to open the slides. Where are the slides? So it's here, but I want to open it in a normal viewer. HSC, it's going to be HamPath slides here. And I will share it also to the Zoomers. Share screen, path, share. Okay, so HamPath is a Hamiltonian path problem, and we'll consider Hamiltonian path questions for directed graphs. So for undirected graphs, this will look actually similarly, but it's technically harder. Maybe we'll comment in the end of this lecture if we'll have time. And also we consider graphs where we have two fixed vertices, which are denoted by S and T, and we consider paths only which start from S and end on T. This is not actually a significant restriction, because you can take a graph with designated vertices S and T and just add some tails, and new S and new T. In such a graph, the Hamiltonian path will have to start in these vertices. So this is basically the same, but this is just for to make the encoding easier. And we denote this problem by HamPath, Hamiltonian path. And the theorem we're going to prove now is that it is an NP-complete problem. So we know from the exercises last time that the Euler path is polynomially decidable. Well, it's very easy to decide the existence of an Euler path and the decision problem, and also to find it. So it's a polynomial time fast algorithm. For HamPath, again, it's a decision problem. So we're not asked to obtain the path. We're only asked to guess or answer whether such a path exists. And even this is hard. It's NP complete. So the fact that it belongs to NP, well, we already discussed it, it's easy. That there are two ways of showing this, by using any of the definitions of the NP class. So if you use the definition with hints, so this is someone who will give you the hint and they will just check that it's correct, then this hint is the path itself. So the path is an object of polynomial size, and also checking that this is a correct Hamiltonian path, that it uses each vertex exactly once. That's actually, and this is a path, that it means that it goes along the edges. This is done easily by a polynomial time algorithm. You can also do it as a non-deterministic computation, which means that you just non-deterministically guess your path. So at each point, you just make a non-deterministic step, hoping that you will obtain a Hamiltonian path from S to T. Well, since you are in the angelic situation, the angel will suggest you the correct non-deterministic execution. So it trivially belongs to NP. Well, all the path also belongs to NP, but it also belongs to P. Maybe here you will also have polynomial time algorithm. Well, presumably no, unless you believe that P equals NP. And NP hardness is proved by backwards reduction. And here, actually, this is included in our lectures for you to understand once more that the reduction should be backwards. So you should reduce a known NP hard problem like 3-SAT, for example, which we discussed last time, to HamPath, not vice versa. So it's easy to see that if you can reduce HamPath to SAT. You can just encode your Hamiltonian path, the existence of a Hamiltonian path, as a Boolean formula. And if you manage to satisfy it, then satisfying assignment will somehow encode the Hamiltonian path. But it's not the direction you wish. Because if you reduce Hamiltonian path to something hard, this will not mean that Hamiltonian path is hard itself. Maybe it's just easier. But you have to reduce a hard problem to HamPath. This will show that HamPath is also hard, because if HamPath were easy, then 3-SAT were easy, but we know that 3-SAT is hard. So this is sort of, in this negative computer science, it's a total negative vice versa reduction, all the topsy-turvy world here. And backwards reduction means that we have to construct a function, polynomially computable, that for each 3CNF constructs a directed graph, which was, it's f of phi is denoted by g subscript phi, which has the following property, that this graph enjoys a Hamiltonian path between two designated vertices. You should designate them, if and only if the formula is satisfiable. So we should encode our formula as a graph, such that satisfying assignments will be in one-to-one correspondence with Hamiltonian path. Well, not one-to-one, but the existence of a satisfying assignment will yield the existence of a Hamiltonian path and vice versa. And I will show you the construction. So the construction is quite easy to understand, but it's extremely hard to guess. So this, I don't remember who was the author of that. One of the classics, like Karp or someone like that. So this was just a matter of mathematical creativity to do this. But once you have done it, you can just admire its beauty. So for each variable, so we have m clauses inside our CNF, and we have n variables. And for each variable, we introduce the following subgraph called gadget. So I hope I think you don't see the arrows. So, but let's see like this: SI. There are arrows going from SI to these two nodes on the sides of this gadget. All these go to TI. So this is local start and end. And here you will have one path which goes to the right, and the other path which goes to the left. So these are interconnected. And for each variable, you introduce two vertices, and also in between there are unnamed vertices for each clause. U1, U2, and there are m of them. So there are 3m plus 1, I don't know, vertices inside this line. And a gadget can be traversed in two ways. So there is the green path, which you have to go to the left, then traverse this stuff to the right, and then go to here. Or you have the red path, which goes right, then it returns to the left, and then goes back. And this is that's the only two ways of traversing the gadget in a Hamiltonian path. Because recall, you have to visit all these vertices exactly once. So this means that either you go to the right or you go to the left. If you go inside and try to return, you fail because this vertex will be visited 2 times. If you choose not to visit these guys, you also fail because you have to visit. And this will be, green means true, red means false. This will correspond to the assignment of value number I. I'll show it like that here, just for you to see it. So if we consider value xi as true, we will traverse this stuff to the right using the green line. If it is false, we'll traverse it backwards. So the encoding inside a Hamiltonian path in the globe, so we'll have a big graph, it will be somehow built from these gadgets. And in this graph, the assignment is encoded as follows. For each variable, we take the ith gadget, the gadget number I. And for this gadget, we see how it is traversed. If it is traversed greenly along the green lines, then we'll say that this variable is assigned to be true, 1. If it is traversed backwardly on the red line, then we'll say it's false. So the Hamiltonian path encodes the satisfying assignment. And then you will need to construct a graph in such a way that, well, now it just encodes some assignment. But now we have to construct the graph in such a way that this assignment will be required to be a satisfying one. Otherwise, it will fail. Well, what we have to do next, we have to use our data from phi, from the CNF. We have to use our clauses. Now we have only used our variables. We don't know clauses. We have the number of clauses encoded here, but not the clauses themselves. And how do we encode them? So if we have a clause Cj, we add a designated vertex, which is denoted by Cj, one of the m clauses. And suppose that it includes xi. So here the ith gadget, we see it here. We see this Cj as an extra vertex, which is the same for all the gadgets, of course. And now we take the following. We take uj, we go to Cj and go backwards to Vj. So inside this gadget, we have the specific zone for the clause number j. And if the clause includes xi positively, then we have to include it inside the green traversal. So green line goes like here. It goes from SI, then it goes to the left, then it goes. It reaches UJ. And now we have the option to visit this CJ also. But we cannot visit this CJ on the red line, because on the red line, you have to reach UJ, then you will go to CJ, oops, you will return to VJ, which you already have visited. So this means that CJ can be visited only on the green traversal of this stuff. And usually, if you include it negatively, then it's symmetric. You will get on the red line, and you go here, you go to CJ, return to the red line. But on the green line, you cannot do this because you will go to VJ, go to CJ, and return to UJ, which is already visited. And now what is the idea? The idea is that you have to satisfy each of the clauses. In order to satisfy a clause, you need to satisfy at least one of its literals, right? And this means that you have to visit CJ on at least one of the gadgets. Well, actually on exactly one. So once you have visited one time, it's all visited. You don't have to, and you are not allowed to visit it once more. But this means that for each CJ, you should have a gadget which allows traversing this CJ on the blue or red or green line. So this means that if you traverse it on the green line, this means that this particular variable which corresponds to this gadget is assigned as true. And this means, and inside your CJ, you will have it positively, just like in this picture. So that means that in your assignment, Xi will be true, and therefore CJ will be true because it includes it positively. Dually, if it is assigned as false, then you will set the CJ will be satisfied by not Xi. So this is the trick. You encode your satisfying assignment using your gadgets. And now, yeah, so if CJ includes Xi, then it can be visited while traversing the ith gadget, but only on the green path. So you traverse the ith gadget and you visit it on the green path. And if it's not Xi, you visit it on the red path. And since CJ should be visited, then you have to satisfy at least one of its literals. And as CJ is a CNF clause, it's a disjunction, it's sufficient to satisfy CJ. Right? So this is the core of the construction. And now we have to actually connect the gadgets into a big graph. And we connect it as follows. So we start with S1, which is going to be S. This is a gadget. Then you identify S2 and T1. So, and next. So let me maybe draw a picture of that for things, maybe for visual. Oh, sorry. This is not the case. That's the thing I wanted to do. Help me, please. Okay. So let me close that. Okay. Let me close this. I don't need this. I hope that people in the Zoom are still viewing this. Annotated, and I will draw. So so the gadget. So this is, I draw the gadget schematically like this. So it starts with S1 and ends with T1. So here will be this thing, and they also are connected to some CJs here. Next, you will just say that this S1, oh, you don't see it, sorry. Stop sharing, and let me share it once more. Share, yeah, I hope you can see it now. I will annotate it, draw. Hope now we can see it. So this is gadget number 1. It starts with S1 and goes on T1. And here you will have these guys which connected to C's, so CJ here. Here you will have another one. So here will be T2, and this is the same as S1, and so, and finally you will reach to T. So again, these gadgets can be connected in. So it can be done like this, for example. So this means that CJ could include, for example, here it includes the first variable positively because it traverses on the green one. So it goes this, so this X1, or not X2, maybe, or something else. It could be include the third one also. So far, so good. So now, how do we traverse this big graph as a Hamiltonian path? So suppose we wish to traverse it. So when we traverse it, we have to start at S1 and reach T. So we have to traverse all the gadgets. And also we have to traverse all these C nodes, closed nodes. So suppose we traverse the first graph negatively, or positively, for example. Or maybe let's try to do it negatively. So when we do it negatively, we go like this, and like this. And we cannot visit this CJ because it's positive. But we could visit some other CJ, some CK if you wish, you can do it, but you don't. So we did not satisfy this because it's 0 and in CJ it should be 1. So now to satisfy CJ, I want to satisfy not x2, but this means that I have to choose the red line also here. On the red line, I will do this, then I will go visit CJ. It's already visited, return here and go here. And continue. At some point, I could take the green path. So if I have taken the green path in the first one, so if I wish to do like this, then practically I could visit this. But I also refrain from doing this because it's already visited on the second gadget. So I will just skip it and go here, and then I will use the red one. So here, in order to satisfy CJ, I could do anything for x1, provided that x2 is negative. Or I could just say that x1 is positive, traverse it by the green one on the first, and then I don't need to do this, and I cannot do it on the second one. So, okay. So we connect the gadgets, and there exists a Hamiltonian path from S to T inside G phi, if and only if phi is satisfiable. So this finishes the proof of NP hardness of the Hamiltonian path problem. So let's recall the general idea that we have reduced that. So we have the 3-SAT problem, which is known to be NP hard by what we call Satin's reduction and Cook-Levin theorem. So here we could say that, let me also write an annotation here. Draw. So we will have just SAT. So, how can we? Let me just first clear all drawings. What did I do? Clear. Okay. So annotate, draw, okay. So we have set here, which is less or equal polynomial m to 3 set. So this is NP complete by Cook and Levin. This reduction is due to Satin. And now what happens? So what does mean that it's NP complete? So this means that this is reducible to A, where A is arbitrary NP problem. So any NP problem can be reduced to SAT. This is Cook-Levin, which we discussed last time. Now SAT can be reduced to 3-SAT, and is done as follows. For each formula phi, you can generate a 3CNF, which is equisatisfiable. It's not equivalent, but it's equisatisfiable. Now, by the construction which we have shown today, this 3-SAT can be reduced to Ham path. So you will have a function which reduces any 3-SAT. Actually, it's not. You can, instead of 3-SAT, you can just write an arbitrary CNF set. It's important that the formula is in CNF. It is not important that it is 3 CNF, that it includes 3. You can also do it through CNF. It's also reusable to a Ham path, but it's useless because true CNF is polynomially decidable, a Ham path is not. So what happens here? You will see that if you have an arbitrary NP problem A, by this chain of reductions, it can be reduced to Ham path just by a composition of these reductions. So for each NP problem, you will have a reduction to SAT. So you will have a function that says that, okay, this is the problem is solvable if and only if the corresponding Boolean formula is satisfiable. This Boolean formula is from Cook-Levin. It's this encoding of the Turing machine protocol and stuff like that. So next, you will do the reduction from SAT to 3 SAT. So you will make this formula equisatisfiable with CNF, 3 CNF. Then for this problem, for this 3 CNF, you will consider, you will generate a graph G5, which is which has a Hamiltonian path if and only if the formula is satisfiable, if and only if the original formula was satisfiable, if and only if the answer to A is yes. So in this chain of reductions, you will show that any NP problem can be reduced to seeking for Hamiltonian path. So if you have an NP problem, any sort of, you can reduce it to the problem of Hamiltonian path. So this is quite an indigenous thing that you started from an arbitrary NP problem. So it was about something and we don't know what was this problem. But we reduced it to search for Hamiltonian path, a concrete graph theoretic question. So you see that this language of graphs is in a sense quite general. So using graphs, you can talk about formulae, you can talk about Turing computations, stuff. So it's all these sorts of things can be done in Hamiltonian path problem. Well, Euler cycle is not the same. Search for Euler path does not encode these things as here. So this is the NP completeness thing. So, okay, I will stop this sharing. And we still have some time left of our class today. I will briefly say what's going to happen in the future. So next class will be the last lecture, the last seminar. So at the lecture, we'll discuss the following. So what will go a bit beyond the NP class as NP class as the class of decision problems and go for things which we will say. So here at the whiteboard, I will clear it and I will draw something here. So we'll talk about a bit of white lines and we'll talk about first, we will talk about this is the main topic for the next lecture, the counting problems. We'll also recall, we talked about it a bit, but we'll also recall search problems. And the third one, we will talk a bit about polynomial delay. So the running example will be satisfiability. And the idea is as follows. So, so the zero we were discussing before, this is a decision. So it's a decision problem, which is in NP. An NP decision problem, it instantiates a search problem. So what does it mean, the decision problem? Decision problem means that you will have something like x belongs to A, or A of x, or I think wrote in this way, A of x is true. That our result is 1 if and only if there exists a hint y such that R of xy. Well, and the size of y is bounded polynomially, because otherwise we can find a very long hint. So this y is called the witness or the hint. This is the NP witness, and it usually has a very nice meaning. For example, in SAT, it is the satisfying assignment. In Ham path, it's the path, stuff like that. So we are usually interested not only in answering the decision question. So the decision question just tries to find out whether such a y exists. But the search problem says, okay, I want to obtain such a y. If the answer is yes, I want to give me an example. This is the search problem. And we have discussed that the search problem, if p equals np, it's also polynomial decidable. So if we can do decision, we can also do search. We did it on the example of the CNF or 2CNF, for example, if it is really polynomially decidable. So what about the counting problem? The counting problem is the other question, how many witnesses are there? So for counting problems, we are interested in the following. This is I will write it like this. The cardinality of the set of y's such that R of xy. Or people sometimes also draw it like this, the number of y's such that R of xy. And the class of polynomial, say, NP counting problems is denoted by the sharp P. This is the class of counting problems which corresponds to NP. So this means if you have an NP problem, you have a harder problem which is counting, because if you can solve this, if you can calculate the number of witnesses, you can then just compare this number with 0, and this number will give you this comparison will give you the answer to the decision question, right? There exists a Hamiltonian cycle. It's the same as there is more than 0 Hamiltonian cycles. But these problems, the counting problems, tend to be harder. Next time we will find an example of a problem which is NP, well, which it's the decision question is polynomially decidable, while the counting problem is hard. That means that unless P equals NP, this problem is not polynomially solvable. And finally, about polynomial delay. It's an extension of the search problem when you want to yield all the witnesses. Again, a caveat that the number of witnesses can be exponential, and therefore just yielding all of them polynomial time is impossible, but we yield them with polynomial delay. At each point, we yield one, and the delay between them is polynomial. We'll also discuss this a bit. We started discussing this last time, but so the central part will be counting problems, and the idea which will actually make a supporting argument next time, that counting could be harder than decision. By the way, there is also a funny class which is connected to counting problems, which is denoted by P, called PP or plus P, or PP. These are classes which are called parity polynomials. So you will, even calculating the parity of the number can be hard. For a polynomially solvable decision problem, calculating parity could be uneasy. So this is the last digit of the number. So you don't know how many there are. So you can solve a decision problem, but don't know are there an even or odd number of. So this is about. We'll make a theory of reductions for these guys and show how this also some sort of theory of completeness, which in a sense represents NP completeness, but it's a bit different. So okay. That's about all for today. So we end a bit earlier because we started on time, which is unusual for us. The first lecture in the day, it's hard to start on time. So thank you for your attention. As usual, I will try to do the streaming for the seminar, so please stay tuned. And this is the end of today's lecture. Thank you very much for your attention.